We will study about the optical properties of advanced materials. Here is list of some optical properties like absorbance. First is absorbance. How strongly a chemical attenuates light. In a substance, when light fall on the substance, some portion of light is absorbed and some portion of light is emitted without absorption. And the amount of light which is absorbed, it is related to absorbance. Absorbance, how strongly a chemical attenuates light. Attenuates light means it decreases its intensity because some portion of light is absorbed by the sample. Birefringence is the optical property of material having a refractive index that depend on the polarization and propagation direction of light. It is optical property of material having refractive index. So when a material has refractive index, and this refractive index depend on the polarization and propagation of direction of light, then this property is called birefringence. Luminosity. It is the amount of electromagnetic energy a body radiates per unit time. Every body radiates some amount of electromagnetic radiation. Some body emit more electromagnetic radiation and some body emit less electromagnetic radiation. For example, a tube light emit more electromagnetic radiation. So this is called luminosity of the material. It is the most frequently measured in two forms: visual, visible light only; bolometric, total radiant energy, which is other than visible. Photosensitivity is the amount to which an object reacts upon receiving photon, especially visible light. Photosensitive, some substances are photosensitive when visible light photon fell on them. There come some chemical changes in rearrangement, and this is called photosensitivity. A substance or object react upon receiving photon. This is called photosensitivity. Fifth property is refractive index, and you have already studied about the refractive index in the previous classes, and it is equal to C divided by V, velocity of light in vacuum, velocity of light in the medium. This is every medium has a different value of refractive index. Scattering of light. You know well about the scattering of light is a general physical process where some forms of radiation such as light, sound or moving particles are forced to deviate from a straight trajectory. They are forced to deviate from the straight path by one or more paths due to localized non-uniformities in the medium through which they pass. For example, when light photons scatter with some body, light photon is traveling in the straight line and it is hit by some dust particles. It scatters, it changes its path, and it is scattered with some angle. This is called scattering. Transmittance. Transmittance is related to amount of light transmitted without absorbing through a medium. Transmittance of the surface of a material is its effectiveness in transmitting radiant energy without absorbing, just transmitting. For example, a transparent glass transmits all of the visible radiation. It is the fraction of incident electromagnetic power or electromagnetic radiation that is transmitted through a sample in contrast to transmission coefficient, which is the ratio of the transmitted to incident electric field. This is about transmission coefficient, and this is another term, and here is the definition of this term: ratio of the transmitted to incident electric field. Well known on the basis of optical properties of material, some optical devices are made, and some of these devices are laser, LEDs, phosphors, and we will study about these devices. The interaction of light with atom. How light interacts with atom, what changes are taken, what changes take place in the material when the light interacts with the material. When an atom absorbs a photon of light of the correct wavelength means for every atom there is a ground state and there is excited state. and there is a difference in energy which is delta E, which is different for different atoms. If the photon which fall on this atom has energy equal to this or greater than this, then this photon will be absorbed, and this will cause excitation of electron from ground state to excited state. So that is why here is written correct wavelength of photon. It undergoes a transition to a higher energy level excited state. Electron or atom goes into excited state. This is the ground state of atom, and this is the excited state of atom by absorbing photon of correct wavelength or correct energy. It is excited. The electron will only absorb the photon if the photon energy matches that of the energy difference between the initial and final electronic energy level. Photon will be absorbed if the photon energy is equal to this gap of energy, and a certain rule known as selection rules are obeyed. In light atoms, the electron cannot change its spin, and its orbital angular momentum must change by 1 unit. A lighter atom has more attraction of nucleus, so when electron goes into excited state, here the electron cannot change its spin, and orbital angular momentum is changed when electron is moving in orbital, and there is something which is moving in a circular path. It has always an angular momentum, so its angular momentum, orbital angular momentum, change by 1 unit. So there is no change in spin quantum number. Delta S is equal to 0 for light atoms, but orbital angular momentum changes by 1 unit, plus minus 1. It can increase by, it can be plus 1 or it can be minus 1. And the spin and orbital angular momentum are not entirely independent. When an electron is spinning, angular momentum is produced. When an electron is revolving in an orbital, angular momentum is produced. So these two angular momentum are not independent to each other. They are related to each other, and coupling between them allows forbidden transitions to occur. Coupling between them, if they have the same spin angular momentum and same orbital angular momentum, then there will be forbidden transition. Forbidden transition mean the type of transition, there are some rules, some selection rules, and if these selection rules will not be followed, then transition will be forbidden, energetically unfavorable. But the probability of an electron absorbing a photon and being excited to forbidden level is much smaller, because forbidden level excitation is energetically unfavorable. So electron normally do not go into forbidden level after absorption of photon. So probability of going into forbidden level is much smaller than the probability of going into an excited level. Here are some examples about allowed and forbidden atomic transitions. So first we will see a simplest example of helium. This is helium. This is example of helium. So in helium, we see that the orbitals are 1s, 2s, and 2p. When helium is in ground state, then it has the electronic configuration 1s2. One electron is clockwise, another electron is anti-clockwise. Angular momentum will be positive, another angular momentum will be negative. When helium absorbs a photon of some energy photon, it is given which is equal to the difference of it absorbs the photon, and the photon energy is equal to the difference of energy between 2p and 1s. The difference of the photon energy is equal to the difference between the energy of 1s and 2p. Then one of these electrons is excited and goes into 2p. This is the excited state of helium, which is allowed. Allowed means Here there are so much selection rules, and one rule here is the one electron which is in ground state is clockwise, its spin is clockwise, and the excited state electron does not change its spin is anti-clockwise. So these spins of both are not paired up. If these spins will be paired up mean they will have the equal spins, then this state will not be allowed state. But here this electron is a clockwise spin and anti-clockwise spin, so this transition is allowed transition. And here is the case where is forbidden transition. It is again helium 1s2 2 electron, and when photon is absorbed, the electron jumps and goes into 2p, but in the 2p it reverses its spin. So we can say both the electrons are in clockwise spin, and which is energetically unfavorable, so that is why this state is forbidden state. And we have studied that there is more probability for the electron for allowed level transition as compared to forbidden level transition. And the next simplest case is for oxygen. This is the case for oxygen for allowed transition. Oxygen has electronic configuration, outermost electronic configuration 2p4. There are 4, this is the electrons in ground state. In the 2p subshell, 4 electrons are present in ground state. And above the 2p is 3s subshell. So when photon is absorbed, which has the energy which is equal to the difference between the energy of these two subshells, then one of the electron will go into the excited state and will not change its spin. So this is allowed transition, and there are more probability for allowed transition. And here is the forbidden transition, and you can see how this is forbidden transition. Forbidden transition is that when this is a ground state electronic configuration of oxygen atom, and when photon is absorbed, these will be paired up. There are these 4 electrons, and these 4 electrons will be paired up, and this is energetically unfavorable against the selection rules, and this is forbidden, and there is less probability of electron, less probability that absorbing photon will cause this forbidden transition. This allowed transition will take place. I think these 2 examples are enough. Excited electron return to ground state. In excited state, atom does not stay for much longer time. It finally return to ground state. The electron may simply emit a photon of the correct wavelength. When the electron return to ground state, atom return to ground state, a photon may be emitted, and this photon may be of correct wavelength sometime after it has been excited. That is, the photon with the wavelength of photon which was absorbed will be equal to the wavelength of the emitted photon, and this is known as spontaneous emission. Here in this diagram, spontaneous emission is shown. An electron of an atom is in ground state, and ground state energy is E1, excited state energy is E2. When the photon which have the energy equal to delta E, difference between the energy of these 2 levels, this photon is absorbed. Then an electron is excited to E2 state. And when this electron return to ground state, it emit a photon of correct wavelength sometime after it has been excited. When an atom is in excited state, a second photon may come along and instead of being absorbed may induce the photon to emit. Sometime another thing can happen. Sometimes this thing can happen that this electron will simply come in ground state and photon will be emitted, but sometime before coming into ground state, This is not, this is again the same diagram of this. This electron does not come into ground state. This electron is in excited state. A second incident photon fall on it. And due to second incident electron, due to de-excitation, a new photon is emitted, and which is in phase with the incident which was first photon. When the atom is in excited state, it returns to the ground state. The electron may simply emit photon of the correct wavelength sometime after it has been excited. This is known as spontaneous emission. Here the spontaneous emission is shown. Incident photon is absorbed and the electron goes into excited state. When the electron returns to again ground state, a photon is emitted of the correct wavelength, which was the wavelength of the photon which was absorbed. And this is known as spontaneous emission. When simply electron goes into excited state and again return to ground state, then the emission of photon is called spontaneous emission. But there can be another type of emission which is induced or stimulated emission, which play a role in the action of lasers. How it can happen? When atom is in excited state, a second photon may come along. When this atom is in excited state, a second photon can come along. And instead of being absorbed, may induce the photon to emit. The second photon is not absorbed because it comes on this excited state. This second photon induced the photon to emit, and this is known as induced or stimulated emission, and this play a role in the action of lasers. The emitted photon in this case is in phase with traveling in the same direction as a photon inducing the emission. Two photons are in the same phase, that their troughs and their crests are in the same phase, and the photon, the resulting beam of light is said to be coherent, and which will be the laser light. And there is another possibility: when the excited electron return to the ground state, spontaneous emission may take place. When the excited electron return to the ground state, induced or stimulated emission may take place, and non-radiative transition can also take place. That electron will simply come to ground state and energy will be wasted in some collisions, or it may be wasted as heat. This is called non-radiative transition. There is no photon will be emitted. Ruby laser. Ruby is corundum. This is an ore. This is one form of aluminum oxide. It has 0.04 to 0.5% chromium ion, which are present as an impurity. And these chromium ion as impurity replace the aluminum ions. The aluminum ions and hence the chromium ions occupy distorted octahedral sites of this geometry. Chromium ion has 3d electron, and in the ground state, these occupy separate orbitals with parallel spins. Like this, 3d electrons, one electron here, one electron here, one electron here, which are separate, which are present in separate orbitals and which have parallel spins. When light is absorbed, one of these electrons can undergo a transition to high energy 3D level. Here is shown splitting of D level in an octahedral site in a crystal. So the chromium which is present in the ruby laser as impurity has 3 electrons, and this is crystal field. This is splitting of D level in an octahedral site in a crystal. You have studied it in crystal field theory. These are triply degenerate orbitals and these are doubly degenerate orbitals. Okay. In the ground state, the 3 electrons of chromium will be here. But when photon of exact energy is absorbed, one of these electrons will jump into high energy 3D level, doubly degenerate 3D level. The chromium ion could now simply emit radiation from of the same wavelength return to the ground state. So electron from here, when returned to the ground state, the photon of same wavelength can be emitted. In ruby of fast radiation, less transition occurs, in which excited electron loses some of its energy and crystal gains vibrational energy. Radiation less transition occur means energy is lost as in collision, vibrational energy is gained. There is no radiation emitted, in which excited electron loses some of its energy, not all of its energy, loses some of its energy, and the crystal gain vibrational energy. Some of the energy is converted into vibrational energy. The chromium ion is left in a state in which it can only return to the ground state by a transition in which an electron changes its spin, because some of its energy is converted into vibrational energy. Here the states of chromium ion involved in ruby laser transition are shown. When electron absorb energy, it goes to high energy level and some of its energy is lost and it come into energy 2 state, where some of its energy is converted into vibrational energy, so it has less energy as compared to this state. So it is about this state. In this state, electron can only return to the ground state by transition in which an electron changes its spin. Here, it can only come to ground state by changing its spin. If it is clockwise, it will become anti-clockwise, and if it is anti-clockwise, it will become clockwise. And we have studied already that changing of spin is forbidden. Such transition is doubly forbidden because it still breaks the rule that forbid and even less likely to occur than the original absorption process. A considerable population of state 2 can build up. Previously, we have studied about state 2. Electron loses some of its energy, converts some of its energy into vibrational energy and come into state 2. And in state 2 is from state 2 to come in the ground state is forbidden. So there is more lifetime for state 2. So the population of state 2 can build up. More number of atoms goes in state 2 and there is population is built up. When eventually, about 5 milliseconds later, some ion in state 2 return to the ground state, returning from state 2 to ground state is forbidden. So it takes much time. The first few spontaneously emitted photon interact with other ions in state 2 and induce these to emit. So first few emitted photon interact with the other ions which are in excited state 2 and induce these excited ions to emit the photons. So the resulting photon will be in phase and traveling in the same direction as spontaneously emitted photon and will induce further emission as they travel through the ruby. And the ruby is in a reflecting cavity so that the photons are reflected back into the crystal when they reach the edge. And they are collected, the ruby is in a reflecting cavity, no photons are lost, they reflect back in the cavity, all the photons are collected in the cavity. The reflected photon induce further emission. Induced emission further takes place. The reflected photon further attacks on the ions which are in state 2, whose electrons are in state 2, and induce them to emit photons, and in this way all the photons are in phase to each other. An appreciable beam of coherent light is built up. The mirror on one side can then be removed and pulse of light emitted. Mirror is present there for reflection of photons. So when the mirror is removed, a pulse of light is emitted, which is the laser light. The high intensity flash lamp, this is the ruby laser, and on the ruby laser for the first excitation is a flash lamp. A high intensity flash lamp excites the chromium ion first from level 1 to level 3 and 4, which we have previously seen in the slides. The lamp can lie alongside the crystalline rod of the ruby or be wrapped around it. The lamps can be around the ruby or lamp can be wrapped in. At one end of the reflective cavity surrounding the ruby crystal is Q switch. This is the Q switch, which switches from being reflective to transmitting the laser light and can be as simple as a rotating segmented mirror. When this Q switch open, the laser beam comes out from this cavity. This is the second topic, that is phosphors in fluorescent light. Phosphors are solids which absorb energy and re-emit it as a light, visible light mainly. Emitting process is spontaneous. In the laser it was stimulated emission also, but here all the emitting process is spontaneous. Applications of phosphors. Phosphors are used in LCD, fluorescent light tube, etc. Fluorescent light produces radiation in the ultraviolet by passing an electric discharge through a low pressure of mercury vapor. The tube is coated inside with a white. This is about this fluorescent tube is present inside this bulb. So this explanation is about this fluorescent light or fluorescent tube. Fluorescent tube radiation in the ultraviolet. Inside it, ultraviolet radiations are produced by passing an electric discharge through a low pressure of mercury vapor. Inside are mercury vapor or any other gas. So when electric discharge is passed, ultraviolet radiation are produced in the gas which is present inside this tube. The tube is coated inside with a white powder. This white powder, what is the function of this white powder? This white powder absorbs the ultraviolet light. Ultraviolet light, which is produced inside by the gas or mercury vapor, this ultraviolet light is of no function because we need visible light from this bulb. So how ultraviolet light is converted into visible light? The ultraviolet light is absorbed by this white powder. And this white powder is a fluorescent material. This white powder absorbs the ultraviolet light and its atoms are excited, and when its atoms are de-excited, visible light radiation is emitted. Alkaline earth halophosphate such as calcium phosphate, calcium fluoride are used as a fluorescent material, white fluorescent material here in the bulb. Usual dopants are transition metal or lanthanide. In this material, doping is also done, and transition metal or lanthanide are used as a dopants. In a phosphor doped with manganese and antimony ions, the ultraviolet radiation from the mercury lamp is only absorbed by the antimony ions because dopant is used, antimony or manganese. The excited antimony ions drops down to lower excited state via non-radiative transition. First, they go to antimony ions. When absorb ultraviolet light, they go to a very high excited state. And from the very high excited state, they lose some of the energy in non-radiative transition, and that is that they can lose energy in collisions, and they come down into a relatively lower excited state. Emission from this lower excited state from this lower excited state, when they come into ground state, visible light photon is emitted. Lower excited state produces a broad band in the blue region of the visible spectrum. Some of the energy emitted by antimony travels. This antimony produces, if antimony is doped in the fluorescent material, then blue light will be emitted from that bulb. By then, because antimony produces a wavelength of blue light. Some of the energy emitted by antimony travels through the host crystal and is absorbed by manganese ion. The excited manganese ion emits yellow light and returns to the ground state. Manganese ion will emit yellow light. The two emission bands together produce something close to daylight. So if we use both of them, if we use one antimony as a dopant, blue light will be produced. If we use only manganese as a dopant, yellow light will be produced. If we use both of them, then some of the blue light will be absorbed by manganese light and manganese ion will emit yellow light. And the combination of yellow light and this blue light will produce something close to daylight. White light will be produced. The incident light is of lower energy than the emitted light, and the process is known as upconversion. Here in the previous example, which was the example of bulb, phosphor material is used in the bulb. The ultraviolet light is produced by the gas in the bulb or by the mercury vapor in the bulb, and that ultraviolet light is of high energy, and visible light is produced by the white phosphor material, and visible light is of low energy. So in the previous bulb example, high energy is absorbed by the fluorescent material and the low energy photon is emitted by the fluorescent material. But here is the case of upconversion. And what is upconversion? When the incident light is lower energy of lower energy and the emitted light is of high energy, then this phenomenon is called upconversion. And in this slide, it is explained how upconversion takes place. In upconversion system, absorption takes place in two stages. An ion absorbs a photon of the incident radiation and goes to an excited state. Here we can draw it. This is ground state. This is excited state. So when a photon of energy, appropriate energy is absorbed, the electron goes into excited state. Okay. Yeah, when an ion is off, photon of incident radiation goes to excited state. It then transfers most of the energy either to another state of that ion or to the excited state of another ion. How it will happen? Here is another ion which is already excited. This electron which is here has the energy and it transfers its energy to the other ion which is already excited. So this excited electron will go further up to more high excited state. And when this more high excited state electron return to the ground state, a photon of very high energy is emitted. A photon of very high energy is emitted. So a photon of less energy is absorbed and photon of high energy is emitted. If this second excited state is metastable, this state is if metastable, there is in between unstable and stable, it has time to absorb another photon before it spontaneously emits radiation. It can absorb another photon and can further go to up level and return to another photon before it spontaneously emits radiation and return to lower state. Before returning to lower state, this can absorb another photon and go even up to higher excited state. Either the absorbing ion or one to which energy has been transferred is now in higher level, whose energy above the ground state is greater than the energy of the absorbed state. Now it has energy greater than the energy of the photon which was absorbed. Emission from this higher level produces shorter wavelength radiation, mean higher energy radiation than that absorbed. So when it comes to ground level, the emitted photon has shorter wavelength or higher energy than the photon which was absorbed.